All right, I guess technically the stuff I just did on the EMF is officially part of chapter 27 as well, but I'll put it in that last video. All right, so chapter 27 is really the culmination here where we're going to say, all right, how do we analyze a circuit? Any circuit, all circuits follow two rules. And you can use these to analyze any circuit whatsoever and be able to solve for just about anything you need to know in the circuit. The first is called the junction rule. It says that the total current that comes into some junction has to equal the total current that goes out of that junction. So current is chosen its name specifically because it seems so similar to water current that would go through, say, a river. And the idea is that, say, on a river, you had some main river and then it split and there was like an island in the middle, so that you now have two branches that go out from it. Well, this is true for water, the amount of current that comes in here, say that current 1, and then we'd have another current going this way, a rate of water flow, and say another one here. Well, the total amount of current that comes in has to equal the total amount of current that goes out, right? So however much water is going through that main branch, the main river, then has to split. Some of it goes on I2 and some of it goes to I3. So that's what a junction rule says. It's just if you come to a place where the electrical current splits, the amount of current that goes in has to be the amount of current that goes out. Or you could have two branches that come together and the amount of current that comes in has to equal the total amount of current that goes out. So the junction rule. The other is a loop rule. So the loop rule says that in any circuit loop, and we'll do a demonstration of this in a minute, the total amount of voltage drops that exist inside that loop have to equal the total number of voltage rises inside that loop. So you could imagine this as being a loop being like a roller coaster ride in gravity, where the total amount of drops in height have to equal the total amount of raises in heights for it to be an entire loop, right? For this to be a complete loop, you have to come back to the same height that you were. You have to have the same amount of ups as you do downs. When you're going along this way, a voltage drop is when you pass from the positive side or the high side of a circuit element to the negative side or the low side of a circuit element. That's considered a drop. You're going from a high to a low, right? Just like a height drop. Whereas a voltage rise is when you go from the low side to the high side of a circuit element. And we're going to do some examples of that right now, and then we'll probably do some more in class. But here, let me follow and do one for a pretty simple parallel circuit. So to actually implement the loop and junction rules, you really need to follow some steps. So the first thing we're going to do when we get a circuit is, and I'll actually put in some numbers here. So for my EMF, I'll say that this is equal to 5 volts, and my R1 I'll say is 1 ohm, and my R2 is 2 ohms. So the first thing I'm going to do is I'm going to label the corners and junctions with letters. So every single corner and every single junction I'm going to label with a capital letter. So I'm going to start here and I'm going to say capital A, that's a corner. Here's an actual junction, B, C, D, E, and F. So every corner and every junction gets labeled with a letter. Then I look at my circuit and I say, all right, how many currents are there here? So let's look at our source here. This is my battery source. So current's going to come out there. and then it's going to come around. It doesn't have any choices. When it gets to A, everything that goes into A has to come out of A, and so that's still the same current coming to there. But now when I get to B, this current would have a choice. Some of the current could go down, and some of the current can go over. And so if I call this, I'm not going to call it I1, I'm going to call this I3. This could be I1, and then this can be I2. When current 2 gets over to C, everything that goes into C has to come out of C. So this is still current 2. And again, it's curling around to here. So this is still current 2 down there. Current 1 goes through resistor 1. And then when they get back to E, E is another junction. So B and E are junctions. All the others are not junctions. Any current that goes into A or C or D or F has to come out of those. And so this current here that comes out when I1 and I2 come back together, this is my current 3 again. Now, here I've chosen the directions. You choose the directions. In this case, it's pretty obvious which of the directions are. Sometimes the directions are not obvious. If you choose the directions incorrectly, you'll get a negative number when you go through and do your math. It's very similar to when we used to do acceleration with forced free body diagrams. Sometimes we chose the acceleration direction wrong, but we'd get a negative number out that would tell us, oh. And it turns out that with an arrow drawn and a negative number, you don't have to change it. That's technically correct. All right, so I've done number 1. I labeled my corners and junctions. I chose that I have 3 currents here. I have 3 currents, I1, I2, and I3. And now, and I've labeled them on my diagram. So you need to do both of those steps for this to work. Not only do you need to do it for me, as showing me the work, but you have to be able to do it in order for you to be able to do the problem. So then I said label all the elements that are in here, the positive and the negative side. All right, so the EMF is obvious, right? The positive side is that side, the negative side is this side. The positive side of a resistor, and this, if we had a capacitor in here, it also usually has an obvious positive and negative side. But resistors, the positive side of a resistor is the side the current enters, and the negative side of a resistor is the side the current exits your resistor. So when I look at resistor 1, current comes in on this side and it exits on that side. For resistor 2, current comes in on this side and exits on that side. So I need to label that for me able to tell whether or not I have a voltage drop or a voltage rise. So this idea of voltage drops means that we're passing from the positive to the negative, and a voltage rise is when you go from the negative to the positive. So we need these labels of positive and negative sides so that we can say, is this a drop or a rise? So now I have my diagram and I'm ready to actually implement my junction rule. So number 4, do a junction rule. And basically, if you've got however many junctions you have, you need an equation for n-1 junctions. So here I have 2 junctions. So I need 1 equation. I need to get a junction rule for one of them. So I'll go ahead and I'm going to use junction B. And again, I'm trying to say that the current in equals the current out. Well, at junction B, the current in is I3. And the current out is I1 and I2. Right? Current in to B is I3. Current out is I1 going down and I2 moving to the right. If I did junction E, I'd have that I2 plus I1 equals I3, which is exactly the same equation, right? It's just the other way around. And so that's why I don't need to do that one as well. It's the exact same equation. Number 5, now I do the loop rule. Loop rules, I need 2 equations here. So the number of currents, so I'm going to need that number, again, minus 1 equation. So here I have 3 currents, so I need 2 equations, or 2 loops. Now we do loops by basically looking at the letters. So it's hard to see both of them at the same time, but I have, I can sit there and say I want to do a loop. So I choose a loop that I'm going to do, loop 1, and I write this out according to some letters. So for loop 1, I'm going to say I'm going to do A, C, D, F, and then I'd go back to A, but usually I don't write that A because I know I have to come all the way back to A. So that means that I'm going to go from A to C, C to D, and then D to F, and then back to A. I'm going to write down a loop rule where I say the voltage rises on one side and the voltage drops on the other. So as I go from A to C, I don't go across any circuit element. There's no drop, there's no rise. As I go from C to D, I move across resistor 2. I go across it this way, and I'm moving from the positive side to the negative side. Right? I'm moving from the positive side to the negative side. So that is a voltage drop. So I say, okay, and again, I'm trying to do voltage drops equals voltage rises. I'm going to go across resistor 2. The voltage drop of resistor 2, or the voltage across resistor 2, is its current times its resistance. That's the voltage drop of a resistor. Then I go from D back to F, and I don't go across anything. And then from F to A, I move across the 5 volt here, and I'm moving from the negative to the positive, so that's a voltage rise. Sorry, my EMF. So this is my equation here. It's not very interesting, probably. And we can actually sit here and say, well, the I2, I don't know. R2 was 2 ohms. And this is 5 volts. And so I2 is 2.5 amps. I actually can solve this for my current. I need to do another loop. I can do any loop I want here. I could do E, F, but I'm actually going to do something different. I'm going to do B, E, D, C. B, D, E, C. So now I'm going to go from B to E, and I'm going over, when I do B to E, I go over R1, and I'm moving from the positive side to the negative side, so that is a voltage drop. I1, R1, and then I go from D to E to D, I get nothing, but then from D to C, now I'm going over this resistor. I'm moving from the negative side to the positive side. So I'm going to say that's a voltage rise of I2, R2. Now I already know that I2R2 is also equal to 5 volts. And so I1 is 5 volts over 1 ohm or 5 amps. Before I move on from this, we actually can come up with a set of rules for parallel equations using junction and loop rules. So if you have a parallel resistors in a circuit, what you can say is that the voltage for all of them will be the same. The voltage drop for all of them would be the same. Because the voltage drop for voltage 1 should be I1 R1, voltage drop for this is I2 R2, vice versa, or all the way through here. What we can see is that the current that each gets, and again, they all have the same voltage, is based upon their resistance. And in fact, it's inversely proportional to their resistance. The more resistance a resistor has, the less current. Because it has a choice. The current has a choice, and it says, why would I go through a higher resistor if I can go through a lower resistor? And in a parallel circuit, it has that option. The total amount of current that comes out is the voltage of your source, or your EMF, which is really what we're calling this V, over the equivalent resistance. But that is essentially I1 plus I2 plus I3, where this is our EMF, 1 over R1, 1 over R2, 1 over R3, again, like this. And so our equivalent resistance in a parallel circuit is very similar to the sum of how we get the equivalent capacitor in a series circuit. You do this inverse sum. And the total amount of current that comes out of your EMF is the sum of all the currents in the branches. Okay, let's do the same sort of thing for a series circuit. So again, as before, I'm going to label all of my corners and junctions. Here's A, B, C, and D. Now in a series circuit, and again, we'll use the same numbers here. We'll say this is 5 volts and 1 ohm and 2 ohms. In a series circuit, there are no junctions, right? And in fact, the current that goes through 1 is the current that goes through 2. We have our current moving like this. All the current is the same current. But I can still do a loop rule. So there's just one loop rule to be made, and that's A, B, C, and D. My positive side of my circuit, of my junctions, of my resistors are these, and here's my positive and negative of my EMF. So as I look at this, I go from A to B, and there's nothing. From B down to C. First I go over R1, and then I go over R2. Then from C to D, there's nothing. From D back to A, I go over the negative to the positive of our EMF. And so it's a voltage rise. They share the same current. And so the current that we get out is the EMF over the sum of the resistances. And again, we can write that as an equivalent resistance, where the equivalent resistance is just the sum of our resistors. In this case, we have 5 volts over 3 amps, or 1 2/3 amps. So for series resistors, they share the same current. In other words, I1 equals I2 equals I3, however many you have in your circuit. But their voltages are not the same. So V1 is I times R1, V2 is I times R2, V3 would be I times R3, all added up. The EMF is the sum of all the voltage drops. But that's also equal to the current multiplied by all the resistances, or the current times the equivalent resistance, where the equivalent resistance, again, is the sum of all the resistors. And the larger the resistance, the larger the voltage drop there is. So the larger that R is, the more voltage it takes to go. So larger resistors have the greater voltage drops. It takes more voltage to make the current go through those larger resistors. And so they have larger voltage drops. Whereas in a parallel circuit, the more resistance something has, the less current it has. And so there really is a real intrinsic difference between what's happening in these two different things. We should have come up with these rules for both of these. This is sort of what we're supposed to come up with after our first lab, simple DC circuits, this idea of what happens in a series circuit and what happens in a parallel circuit. All right. Some circuits can be thought of as combinations of series sections and parallel sections, and that's really what you're doing in number 29, number 49, number 101. I'll do at least some of these in class. I'm not going to do any here, but you can use these rules for series and parallel circuits without having to do in other words, without having to do the loop and junction rules. You can just use these known rules about series and parallel to do number 29, number 49, and number 101. You do not need a junction or loop rules to do those. But what I'll do in the next video is what happens when you do need to do loop and junction to be able to do it at all.